Welcome everyone for last seminar. This organizing at IT for Innovation this year. Welcome everyone here and online. Today's speaker, Dr. Grzegorz Reichel Mieldziot, will be introduce the talk about quantum algorithms and Schrödinger equation. So the stage is yours.
Thanks a lot. Thanks a lot for the introduction. I hope you can hear me with this. Can I have a confirmation that the online people? Great. Thanks a lot for the invitation. It is a great pleasure to be here. And well, actually, I have not come from far because Krakow is 2 hours drive from here, but it was still my first time in IT for Innovation. I hope it's not the last one. Yes, this talk is devoted to introducing quantum algorithms and then showcasing how to use them. Well, what's the motivation actually for the study that we have conducted? Is the something which physicists like, so Hamiltonians and energetic levels. So these are the most important things in the whole, basically, physics, I would say, that to find energies of a different parts of matter. So that's why for this particular problem, we are aiming at applying quantum algorithms to solve it. The caveat is that obviously at the current stage, even powerful quantum computers, as you have here, are not powerful enough to do something better than existing classical supercomputers. So our goal is rather to show what's the path and how to achieve the better accuracy, and what from the computer science perspective, what's important is the scaling. So how as you scale the problem, how will the time, for example, time conditions for the time of running of your algorithm, how it will scale. So in the course, I know that maybe not all of you are familiar with all of the quantum algorithms. So basically, I would say that the most basic two ones are the Grover algorithm and the subsequent amplitude amplification. But there is also gonna be quantum phase estimation introduced in the middle. All right. So what is a Hamiltonian? Well, Hamiltonian is the energy operator of a given system. So what do we know about it? Well, it's Hermitian operator, but usually we don't know much a priori about. I mean, for a given system of interest, we, for example, don't know the energy. Energy is going to be the spectrum of this operator. So in essence, our problem is to find the energies, so the eigenvalues of a given operator. Now, the usual problems with finding these eigenvalues is that these operators are very, very large. So in fact, when you scale the size of your system, for example, electronic systems or interacting particles, basically the Hamiltonian is going to scale, the size of the Hamiltonian is going to scale exponentially. So this means that it's very problematic to tackle this problem. I mean, there are a lot of ways to simplify this problem, and some clever people know how to solve certain cases, even analytically. But in general, it is a very hard problem. So we're not aiming to solve this problem on existing quantum computers, but we're aiming for finding a way to do this on fault-tolerant regime, so without considering the noise that current devices have. Okay, let me start. Before diving into the general problem, let me start with, I would say, the simplest quantum algorithm there is, so the Grover search. Well, this slide is to showcase what's the difference between classical and quantum search. So in classical search, suppose that you are given n elements, and all of them are red, apart from one. But, well, without looking at each of the elements, you cannot tell which one is green, right? You need to look at them. And how many times do you need to look at them? Well, if basically in the worst case scenario, well, it's gonna be at the very end. So in the worst case scenario, you're gonna have scaling of your the complexity of your algorithm is gonna scale as linearly with the size of your set to be searched. Um, so basically, it turns out that you can do better using quantum algorithms. This better is quadratically better, and it is exactly this square root speedup that you have here. Now, let me show you of what this algorithm consists. So basically, the point is, I hope you are all familiar with the notation I'm using here. So what we aim to do is we aim to change the state, which is at first in an equal superposition of all of these states. So the state S, sorry, I cannot use the pointer here. So if you have an equal superposition of the original state, so you may think of it as an equal superposition of all the elements of a set. Well, the problem with this is that this is, well, you cannot tell much by this state alone. I mean, if you now measure this, any element is equally likely. So what you want to do, and our goal, is to transform this original state S into a state which is consisting only of your green element. So your green element here is omega. So we want to find such a transformation which takes S and transforms it into omega with little additions from all the other states. So what do we have at our disposal? Remember that in the quantum domain, in quantum algorithms, we are dealing only with unitary operators. So everything we do must be unitary because these vectors, they need to be properly normalized, and they cannot lose this normalization and orthogonality. So what we first, well, after starting with the initial state 1, so point 1, we go to point 2. So point 2 is basically a reflection, which is to the state basically perpendicular to state omega. So thinking in this two-dimensional picture, you may think that there is S, which is consisting of many states, like n states, and there is omega. So S is almost perpendicular to omega, but it's not perpendicular because it also consists of this omega. But you can find on this plane, you can find also a state which is perpendicular to omega, and then reflect around this state. So what you get from S, well, you get first the state in blue. So omega, U omega acting on S. Well, what happens next is you can again reflect, but now not across the omega state perpendicular to omega, but rather across the starting state. And what you get is now a state in blue on the right. So here, what we have is a state which is slightly rotated to the right direction, right? Because we want to obtain state omega. Now, the question you may pose here is, but is it realistic? I mean, somehow we have some knowledge of this omega, right? We have this reflection around the state perpendicular to the marked one. So why do we actually use anything if we already know what the state is? So this is the caveat of this algorithm, and it turns out that sometimes you can perform some kind of operations on your system, which changes the system according to the state it is without knowing what's the solution that you're looking for. It might sound convoluted, but imagine Sudoku. It is possible to solve Sudoku. Well, it's usually very involved. A lot of people spend hours on that, but it's very, very simple to check if a given solution is a Sudoku. Is a valid Sudoku. We just check every row, every column, and every block, right? So checking for a solution might be much, much easier than finding the solution, right? It's like one of the basic for many computer science problems. So this means that there exist some cases in which you can reflect around the state without knowing what the state is. And it's basically very similar in spirit to verifying that a given solution solves Sudoku or not. So what do you do here next? Well, you apply the same procedure. So you again reflect across this perpendicular state perpendicular to omega. You reflect across the initial state, and you do this many, many times. In the process, you will acquire a phase, right? So you will rotate more and more towards your state. And turns out that if you iterate this process basically square root of n times, you will get exactly your state omega, or something very, very close to that. Which means that applying only square root of n times your algorithm, you achieve something which classically requires a scaling the same as n, which means that there is square root speed up in this quantum algorithm. Now, beware that I'm not saying that this is useful for searching your database. I mean, first of all, you need to encode your database into a quantum computer. Second of all, you actually need quantum computer to be powerful enough. Both of these problems are quite important. So that's why actually, okay, maybe I didn't want to go here. That's why actually it's more important as a subroutine in other quantum algorithms. So in some sense, you're not solving a problem. You don't have your Excel file and you're looking for someone who has name given, I don't know, Barbara, but rather you're using this as a subroutine for a different quantum algorithm, which I'm going to use later on. The second, by the way, if any of you has questions like in the middle, I will be very happy to answer them because it's good to have, well, some kind of back and forth. I hope I'm not losing anyone in the process. So if anyone has a question, please go ahead. Okay, I see maybe everything is too perfect or just people are very shy. I hope the first one. But the second useful subroutine that is used in our algorithm is quantum phase estimation. So you know that we're dealing with eigenvalues. So eigenvalues are very important. Well, for Hamiltonian, as I said, eigenvalues are energies of some systems. So they are useful for applications in physics, chemistry, various points of view. But in the case of quantum computers, as I've already told you, well, there is all of the operations are unitary. So we can also pose the following question. You are given a unitary. And this unitary is, well, unitary matrix. But this unitary matrix can also form, let's say, a quantum circuit. So any quantum circuit can be thought of as a unitary. And now your question is, thinking about this circuit as a matrix, what are the eigenvalues of it? Can we find them efficiently? And quantum phase estimation is exactly an answer to that. So suppose that you are given matrix U, and controlled versions of that. So without going into too much details, controlled gates are those which act on a given qubit. In this case, let's say bottom qubit or bottom qubits, and are controlled on some other qubit, which is written by this line, which is depicted by this line. And basically, anytime the state on this qubit that controls is 0, nothing happens. Anytime the state here is 1, the gate that we want to apply happens. So this is controlled unitary. And now the question is, how can we use this unitary U and controlled version of that to find the eigenvalues? It turns out that the following circuit actually does that. So again, this is not the main scope of this talk, but I'm just gonna advertise to you quantum algorithms because I think it's quite a very interesting topic with potential usefulness in let's hope not so far future. And that's why quantum phase estimation is one of the central things that you wish to study if you do that. So basically, in this case, quantum phase estimation consists of first preparing a state. You know your state psi, and you know that this state psi is in the is the eigenstate of your unitary. And then it turns out that if you prepare a state on the controlling qubits, you can actually, by applying powers of u, of controlled u, and inverting them by using quantum Fourier transform, which basically gets out these eigenvalues, you can measure exactly the eigenvalue theta. That's not, sorry, that's not defined here. That's my bad. But this theta is basically the eigenvalue of psi, or rather e to I theta is the eigenvalue. Okay, so again, I don't want to go to too much detail here, but maybe there are questions. Maybe something is not really clear. Okay, let's go further. So what did we actually do? So now coming to our problem, as I told you, is to find eigenvalues of a given matrix, which is Hermitian, so self-adjoint. Basically, these eigenvalues are going to correspond to energies of your physical system. So the problem with that is that finding at least a single eigenvalue is already incurring costs which are linear in n. You cannot do better. There's no way that you get a matrix which is n by n, and you get at least one eigenvalue with complexity better. If you already know the eigenvalues, then yes. But for a general one, it's not going to happen. So it turns out that you can do better quantumly. And to do so, you actually use this Grover search as a subroutine that I mentioned earlier. So maybe I'm not going to go into too much detail here, but the point is that what we do is we find eigenvalues of some family of Hermitian matrices. So M mod alpha, defined in this equation, is a family of matrices, actually of linear dependence time. So there is constant term M0 and alpha linear, and linear term alpha M1. Okay, so that's a family of matrices. And now, on this plot, let me maybe explain the plot because it's going to be, I think, much easier to understand than the theorem. So, at least at first. So, on the x-axis, you have changing parameter alpha, and these three curves, so green, orange, and blue ones, depict some eigenvalues of a matrix M alpha. So here there's M for one alpha, M for another alpha, and so on and so on. Obviously, eigenvalues change because matrices change, right? But what we want to find is we want to find such parameters of alpha for which the matrix M of alpha has eigenvalue in a region around our lambda 0. I know it might not be visible from the far, but we're aiming to find eigenvalues close to lambda 0. So basically, to find parameters for your family of matrices for which it only calculating the eigenvalues, also the eigenvectors. No, here it's only the eigenvalues. The eigenvectors would be too general. But thanks for the question. So now this basically so basically in this our aim here is to find the eigenvalues in a given range. Now, why is it useful for us? Well, I don't know how many physicists are here, so maybe that might be a little off-putting for the rest. But basically, the point now is to encode our energy operator, our Hamiltonian, into a family of matrices and find then its spectra. So what we do is Hamiltonian usually consists of two terms. So one of them is a term associated with the kinetic energy, that's K, and the other one is associated with the potential energy, that's V. So you can discretize system. Well, sometimes systems, well, usually systems have infinite degrees of freedom. So we don't want to consider infinite matrices because they are too large and nothing can encode them. But if we discretize the system, we can introduce some basis set, and then the problem becomes a problem of finite sized matrices. So eventually what you get is this type of equation. Now, I don't want to go into too much detail again because I'm not sure how will that be received by you. But the point is that we want now to solve this problem. So solve the problem which is on the top. What do I mean by solving the problem? Well, you can find both eigenvectors, the eigenvalues of the matrices, but you usually don't care about this in that much detail. I only care about eigenvalues. So eigenvalues here are stored in E. So this last matrix, this matrix is diagonal. So what you can do, you can invert. You can move basically some matrices to the other side and by inversion, and then diagonalize the resulting H tilde, right? Well, that's one way. The other way would be to go with something which should be maybe more familiar to you now by because I've showed you these eigenvalues, this one parameter family of matrices, which is this. So basically you move right hand side to the left hand side, and you say, okay, so then basically for a given eigenvector, which we don't know, this consists of saying, or rather singular vector, but that really doesn't matter at this moment. Then it consists of finding such parameter E such that this matrix has a kernel which is not trivial. All right. And this basically is the same as we discussed earlier. So we were looking for in instances of parameters, of linear parameters, so think alpha is now E, for which you have eigenvalue, well, the exact eigenvalue. Here, eigenvalue should be 0, right? Okay. Basically, in this case, we have two ways with which we want to approach the problem, or we can approach the problem. Which one is better? Well, the first one consisted of inverting matrices. Now, the only problem with inversion is that it's not always well defined. And actually, that's usually the case in our system, because if the condition number, so basically the relationship between the largest and the smallest eigenvalue of a given matrix is bad, so condition number is high, then matrix is, well, the matrix inversion is very, very sensitive. So actually, small perturbation, well, leads to an error which is quadratic in the condition number, which is bad. Because for the cases we have studied, which are very small cases even, condition number can be 10 to 16. So if you square this number, obviously it's like that big a number that the perturbation is going to be terrible. So what's on the plot? What's on two plots actually. So here I'm considering the very simplest example that physicists study, and that's the harmonic oscillator. I mean, we all have passed physics lessons, so there's always pendulum, there's always harmonic oscillator, and physicists do this all the time when they cannot find anything better and when they cannot basically solve harder problems. So this is what we actually did. The energy structure for a harmonic oscillator is the simplest you can think of because these are equidistant lines. Because energy levels are just multiplicities of n, they're just proportional to n. So first energy is equally distant from the second energy, and the second energy from the third excited energy, and so on and so on. So what do you see here? On the x-axis, there is energy. And in equally distant lines, so the red ones and blue ones, are the energies, the exact energies that we already know. And here I want to showcase which of the two algorithms discussed in the previous slide is better. So the first one of them consisted of inverting the matrices, and actually what we see from the inversion are the red dashed lines. They cover they agree almost exactly with the energy that we already know, the analytical energies. And the blue curve, now this curve which has these dips, is the curve which corresponds to the minimal singular singular value of the matrix, well, of this family of matrices. So we have family of matrices, and for each point, we find the minimal singular value. So it turns out that, well, finding these dips actually correspond quite well to energies. So you may say that both of these methods can work, right? Now, suppose that we want to go farther. So see that here we go only to energy around 20. Well, you can go farther. I mean, arbitrary units, but you can go farther. How do you do that? By increasing the number of basis functions. But then actually it means that the matrices become less and less invertible, in a sense that the condition number now grows to 10 to, as I said, 16. It's not that big system. So what you can see here is that these red dashed lines, they actually disagree completely with the energy structure. So the energy structure is green, and these red lines, well, they may work well for 2 or 3, but they completely disagree with what we want to achieve.
Okay, we have a question.
What is the dimension of the Hamiltonian? So it depends on the system basically here, because in principle, a Hamiltonian here has infinite number of degrees of freedom, but in this case, we discretize it using 26 basis functions. So so it depends on this and the and also the number of grid points with these basic functions. Um, So, yes, I would say that in this form, it's not easy to say what is the dimension of the Hamiltonian because in this case, let me go to the previous slide. In this case, you can either ask what is H tilde, what is the dimension of H tilde, or what is the dimension of other operators. So if you ask about H tilde, then basically this corresponds to the number of grid functions, so it's 26 in this case. Maybe that's the simplest manner to answer the question. And in the other case, it's 36. So it's relatively small systems. So nothing. I mean, should be very easy. But it turns out that using this method already shows you the limitations of this problem, of this type of solutions using inversion. If the well, basically, if the condition number is too high. But comparing with the other method, so finding the minimal singular values, well, what you see is that, well, still you can probe higher energies because these dips still exist. I mean, they don't align perfectly for some cases, like here, it's, well, you don't see anything and you should be seeing some dip. But in general, this method can be used to find the energies for this case. So how do we actually do that? Well, I still haven't discussed the one question because I've been talking all the time about the Hermitian matrices, but as I said previously, well, the unitary matrices are what's being implemented in the actual quantum circuits. So, well, without going into too much detail, let me just say that the way to encode a given Hermitian matrix, or actually any matrix, into your unitary is to encode it into one of the blocks. So suppose that you have your matrix A as here. you just input, you just put it in a bigger matrix. And well, obviously there's a problem. Not all the matrices can form submatrices of a unitary matrix. For example, if the norm of A is too high, it cannot be done. So there are some caveats here that we discuss in the paper, but not in here. But let me just leave it for a second. Okay, how do we then apply this algorithm in a real scenario? So how do we, I said that there is a way to find eigenvalues of your system, or find parameters for which eigenvalues exist that you wish to find, with a square speed up using quantum algorithms. But how do you do that? So actually subroutine for that is you need to apply some algorithm many times. So what is this algorithm? This algorithm is actually the Grover iteration. So Grover iteration, Grover search can be also thought as increasing amplitude or the probability of the occurrence of your of a state of your interest, of a state that you wish to find. So in this case, we want to find the eigenvalue or the parameter. So we need to increase the amplitude, but we also need some circuit or rather subcircuit which selects this parameter. And this is what quantum phase estimation is useful for. If you want to have more details, well, you should go to the web paper, or ask me now. Yes. Well, the last thing I want to mention, because of pedagogical reasons, is that what we aim to do here is not to, as I said, find to solve this problem on the today's quantum computers, but rather to do so on fault-tolerant devices. So what's tolerant? Fault-tolerant quantum computers? Well, they are the computers that apply some error correction, and this error correction is, well, usually thought of as increasing the overhead of your qubits, and this allows you to correct some of the errors. So for example, if you want the code I'm showing here is implementing some 2-qubit CNOT gate by increasing the number of qubits 7 times, right? Because it encodes 2 qubits into 14 qubits. Now, it turns out that there is more to that than just increasing the number of qubits and doing things parallelly, because there is a theorem which says that actually such a way, so applying them in parallel or transversally, is not possible for all of the gates. So we need to do something better. And this actually shows us or at least prompted us to measure the cost of our algorithm. Because in our case, well, we wanted to measure the gate which is the hardest to implement using error correction. And well, currently people usually say that this is the T gate. So T gate is this very simple 1-qubit gate, but actually using the standard error correction codes is going to be 100 or even 1,000 times more expensive than the entangling gate I showed you previously, so CNOT. So then, for us, the number of appearances of T-gate is gonna basically tell you how costly your algorithm is. In this case, our algorithm. So this is the slide from which I only want you to take the blue message. Well, because there is a lot of text and I don't expect you to read this. But basically, this is a comparison of the complexities, which for the classical case are measured by the number of let's say, floating point operations. But for the quantum case, it is the number of T-gate count. And here, what you can see is that in one of the parameters, well, closure parameter, you may say, so the size of your problem, the scaling of our algorithm is better than the classical ones, because we can achieve square root of n, which is better than n squared, or actually n to power 2.371. But computer scientists can say more about it. This stems from the inversion of the matrices. Now, it may sound great, but well, there are a couple of things to consider. First of them is that we don't have that big quantum computers. That's one thing. The second thing is that, well, even if we had, there is still a question of which I haven't touched upon here, because like if you consider a given problem, there is so many parameters that you can tweak and look from different perspectives that actually you need to decide for something. So we have decided to focus on the parameter which is the most, let's say, useful for us, or rather the most descriptive, which is the size of the system. But there is also, for example, precision. So how well can you find these eigenvalues? And it turns out that in this respect, actually, classical algorithms are better. So it may happen that, well, you have matrices big enough, but still the overhead, the most important overhead comes from the precision. But it may happen otherwise. So depending on your system, of your problem, you should consider these things. Like, you cannot just say, usually in these cases, you cannot just say that there is one parameter which describes the problem. I mean, that's hardly ever the case. So in this case, we have focused on the size, but please keep in mind that if you want to apply any of this, there are other things to consider. Yes. Okay, so to sum up, we have found a quantum algorithm which solves a particular problem, which is basically finding a spectrum of a given Hermitian matrix. And applying basically quantum phase estimation and amplitude amplification, we have achieved up to fourth power improvement in the size of a system as quantified by the T-gate complexity, and without having the problem of condition number, which happens often when the matrices are not invertible. But keep in mind that the exact speedup will be dependent on your exact problem and will require fault-tolerant computers. And with this, I'd like to finish. Thanks for your attention.